Good morning, everyone. I'm Jinbo Peng from Fudan University. I'm presenting on behalf of the authors of this work, SignalsforTerrestrial non-sparse multiband signals for terrestrial and non-terrestrial wireless networks. SignalsForTerrestrial is a powerful tool that analyzes wideband non-sparse signals in complex wireless networks. It delivers deep physical layer insights with high efficiency. In this talk, I'll highlight its innovative features and impact on wireless network monitoring. So let's dive in. Wireless networks are the backbone of modern connectivity, powering applications like Wi-Fi, Bluetooth, 5G, and satellite systems. With more wireless networks being deployed, spectrum resources are becoming increasingly scarce, and this drives spectrum sharing in bands like 5 GHz and the emerging 6 GHz. This creates complex, crowded environments and may easily lead to interference and poor performance. Without deep physical layer inspection, network optimization is tough. Our goal with SignalsForTerrestrial is to deliver a powerful tool for detailed monitoring of physical layer network. To optimize wireless networks, it would be helpful to sniff granular details in the physical layer, such as spectrum usage, modulation types, protocol types, signal lengths, and open header information. This information is vital for effective network management, helping us identify potential spectrum conflicts, track signal activity patterns, and diagnose misconfigurations. However, capturing these signals across wide shared spectrum requires high sampling rates and complex processing, which poses significant challenges. Traditionally, the Nyquist-Shannon theorem states that to capture a signal accurately, we must sample at least twice its bandwidth. Since we are targeting the wide 5 to 6 GHz shared spectrum, according to the Nyquist theory, this requires very high sampling rates and gigahertz level. It demands costly, high-speed equipment for sampling, data transmission, and signal analysis. As a result, comprehensive wideband monitoring becomes expensive and impractical for many applications. This challenge pushes us to find a more efficient solution for effective physical layer monitoring. Here we take Wireshark, a well-known network analysis tool, as an example. It's very great for narrowband signal analysis, but it can only sniff one channel at a time due to high sampling demand of the Nyquist sampling. This falls short in today's wideband, multiband environments where multiple signals need simultaneous monitoring. Ideally, in addition to providing detailed physical layer inspections, we wish such a tool can monitor multiple bands simultaneously. Current solutions towards the Nyquist sampling have their own limitations. For example, sequential scanning cannot concurrently monitor all bands and cannot capture enough samples for one specific signal. For compressed sensing and sparse Fourier transform, although they provide detailed information, they only work in sparse scenarios and they fail in non-sparse spectrum. Some other techniques such as S3 from NSDI-21 can perform non-sparse spectrum sensing, but during signal processing, these signals are distorted, so S3 cannot provide deeper inspection such as demodulation or protocol decoding. So here we present SignalsForTerrestrial, our solution for wide and deep physical layer monitoring under low sampling cost. It works with sub-Nyquist radios and handles dense non-sparse signals. SignalsForTerrestrial breaks the sparsity limit by combining deep learning with a novel signal reconstruction scheme. Compared to compressed sensing or sparse Fourier transform, it can capture over 50% more signals with the same amount of sampling resources. Besides, SignalsforTerrestrial delivers holistic inspections. We can use SignalsforTerrestrial to sense the spectrum, recover signals, identify protocols, and decoding headers of these protocols, and extract key information from these open headers. All of this is done with low sampling cost. So how can SignalsforTerrestrial capture signals beyond the sparsity constraint of compressed sensing or sparse Fourier transform? SignalsforTerrestrial changes the traditional sampling limit by rethinking how we recover signals. Classical multiband signal sampling theory says that if we know where signals are in the spectrum, we need to sample at the lambda rate, which is the sum of all bandwidths. If we don't know, which is a more general case, or we call the blind recovery case, we need twice that. Here we show what happens with the standard compressed sensing algorithm SOMP. When the sampling rate drops below twice the lambda rate, signals can't be recovered correctly, as you can see from these arrows and the bottom left, where some signals are missing and some unexpected signals appear. This shows the limit of existing approaches and why we need new thinking to go beyond it. However, is twice the bandwidth sum really needed for blind signal recovery? Instead of tackling blind recovery directly, we break it into two easier steps. First, we sense spectrum occupancy to gather key information. Then, with this, we only need to perform non-blind recovery, where we actually know where the signals are in the spectrum. If sensing spectrum occupancy requires less than twice the bandwidth sum, then the two-stage recovery becomes an easier path, and the traditional sampling requirement isn't always necessary. In the following, we will show that with the power of deep learning, faithful sampling is possible below twice the bandwidth sum. So, building on the idea of breaking down the recovery process, the sampling and reconstruction parts of SignalsforTerrestrial follows such a pipeline. We start with multi-coset sampling, a popular sub-Nyquist method. It captures signals with multiple parallel ADCs and much lower rates. Then, SignalsforTerrestrial uses a deep learning model to predict where signals are in the spectrum. This prediction turns the tricky blind recovery into an easier non-blind task. It's like finding a shortcut in a complex puzzle and avoids the strict need for twice the bandwidth sum. Then we extract each narrowband signal and forward them for further signal analysis. Specifically, our deep learning model is a lightweight transformer network with just two encoder layers. It takes sub-Nyquist samples, embeds them as tokens, and predicts occupancy state for each subband. For signal reconstruction, we use multi-coset samples to build a classic y equals a times x problem, which is similar to compressed sensing. But here is the twist. We use the prediction S from the transformer network to only keep columns of A and rows of X that actually influence Y. This turns the underdetermined problem into an overdetermined one, making it easily solvable by least squares estimation. Moving on to the experimental results of these parts, as you can see in the top right figures, SignalsforTerrestrial shows much lower error rates compared to compressed sensing and transformer-based sorter methods across all SNRs. For reconstruction of unseen Gaussian random signals, as shown in the bottom figures, SignalsforTerrestrial achieves near-perfect reconstruction even when sampling at a rate 33% below the blind sampling rate. In contrast, deep learning-based DCS and compressed sensing-based DTMP result in significant signal distortion. This means that C-Code can capture more signals with the same amount of sampling resources. After signal reconstruction, we still need further back-end analysis for deep physical layer inspection. As a passive receiver in a protocol-agnostic environment, traditional process methods are complex and rely on protocol-specific algorithms such as preamble correlation, synchronization, channel estimation, and so on. SignalsforTerrestrial adopts state-of-the-art ideas using deep learning for protocol identification. Further, we propose to replace the complex decoding process with simple end-to-end transformer networks. We co-design the protocol classifier and the header decoder. First, the protocol classifier takes the reconstructed signals from the previous module. Here, a trainable query token is fed into the transformer decoder layer alongside IQ embeddings for cross-attention. It extracts global information to identify protocols. The intermediate features from the transformer encoders are also passed to the header decoders. This encoder and decoder structure is designed to facilitate feature fusion and the header decoder stage. For the decoding modules, SignalsforTerrestrial treats the decoding process like an IQ-to-bit translation task, similar to natural language processing. Features are fused with intermediate features from the protocol classifier. We also use query tokens for cross-attention, where each token represents a query for a specific bit in the protocol header. This approach unifies the decoding process for diverse protocols such as DVB, S2, and Wi-Fi into a streamlined framework. It only requires protocol-specific adjustments to the network parameters and the number of query tokens, and no need to design new processing pipelines for different protocols. For experiment, we use MATLAB to synthesize training dataset and evaluate the performance on over-the-air signals. Signals are generated and collected with NI USRPs, with monitored spectrum ranges from 5 to 5.8 GHz. We use these real-world datasets with diverse channel conditions to test the C-code's generalizability in practical scenarios. In terms of protocol identification, C-code outperforms the transformer-based sorter T-prime, particularly on over-the-air DVB-S2 signals. T-prime has trouble in generalizing to new data, but C-code maintains over 99% accuracy and high sampling rates and stays strong even at low sampling rates, where R equals to 0.625. These confusion matrices clearly show C-code's superior performance in classified protocols. And finally, we use C-code to decode DVB-S2 and two types of Wi-Fi signals, which is non-HT 20 MHz Wi-Fi and HT Wi-Fi. While working below the blind sampling bound, C-code achieves over 99% decoding accuracy for key fields like modulation and coding schemes across DVB-S2 and Wi-Fi signals. Packet length errors are minimal on the 300 bytes and the 95th percentile, and the signal duration decoding errors of HT Wi-Fi packets are also negligible. Note that all these things, including signal recovery, protocol identification, and decoding, are performed when the number of signals exceeds the capacity of blind subnyquist sampling. This makes SIGCOD highly effective for physical layer network monitoring. In conclusion, SIGCOD expands the capacity of wideband spectrum monitoring. We provide a new method to capture signals beyond the sparsity constraint of blind recovery. It generalizes well to unseen environments and it simplifies protocol identification and header decoding with a deep learning pipeline. We believe SIGCOD offers valuable insights for wideband sampling and deep learning in signal processing. Thank you, and I'm happy to take your questions.
Are there any questions from the audience? Jingbo, don't be shy.
Okay,
can
okay.
show you
Do I need
face.
to open my camera? Yes. Can you hear me?
Yes.
And can you see?
Okay, are there any questions from audience? I gonna, Jingbo, you can hear me, right?
Yes, 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 I can hear you.
Okay. Let me ask you a question. Okay, I noticed that your SIGCOD use transformer to replace the traditional decoding and demodulation. Then may I know that how do you guarantee the real-time requirement?
Okay. In fact, I didn't put the table in my slides. We actually did some evaluations on the inference speed and memory usage of our transformer models, and it actually those components actually can perform their tasks in real time. And although transformers, as we know, they scale quadratically in time complexity, but in our design, those transformer models are very lightweight, and these models do not act in an auto-regressive manner. So all these tokens are processed in parallel, so we can reduce the inference time, and we process the signals by smaller frames, so we avoid the problem caused by long sequences. So that's how we ensure guaranteeing our SIGCOD can perform in real time.
Okay, thank you. And we have an audience who has questions to ask.
Hi, thank you for your talk. This is Kang from UCLA. I have a quick question. Is your model basically like, I'm wondering, is your work can be used for like network traffic generation? I remember there are a lot of work on that. I'm thinking maybe your work also can work on that part.
To make sure you hear the question, so the question is if your work is able to simulate the network traffic.
Simulate is my work simulating the network traffic, or?
I believe it's you were able to simulate the network traffic, right?
Yeah.
No, this work is not to simulate the traffic. Is to SIGCOD is designed to monitor the network. Monitor the network traffic, just like Wireshark do for upper layer networks. And we are doing SIGCOD is a wireless shark, and do I get it?
Okay.
Yeah, because I'm thinking like if you can like monitor the packets, basically you need to also need to understand the packet like pattern or something. Yeah, they maybe also can be used for that. Yeah, thank you.
Yeah, maybe it can be the future work. Okay, thank you, Jingbo. I know it's going to be very late in China. Thank you for staying online with us. And also a big thank you for, with that, let's conclude this first technical session. And a big thank you to all our presenters and also the audience for your questions and engagement. So now you can move to enjoying your lunch and please also enjoying the rest of the program of MobiSys. Thank you.
Okay, thank you.